Hi everyone and welcome back to ARM Processor SoC Part 3. In this video we will continue the remaining part of the Chapter 4. Pipelining is a technique used in modern CPUs to improve instruction throughput and overall performance by allowing multiple instructions to be processed simultaneously. Instead of waiting for one instruction to complete before starting the next one, pipelining divides the instruction execution process into sequential stages, each of which can be performed concurrently for different instructions. Let's break down the typical stages of a pipeline CPU. Fetch stage. In this stage, the CPU fetches the next instruction from memory using the program counter, PC. The fetched instruction is then placed into a buffer or instruction queue to await decoding. Decode stage. The fetched instruction is decoded to determine the operation it specifies and the operands involved. This stage also includes fetching any necessary operands from registers or memory. Execute stage. Once the instruction is decoded, it enters the execution stage, where the specified operation is performed on the operands. This can include arithmetic or logical operations, memory accesses, or control flow changes. Write-back stage. In the final stage, the results of the executed instruction are written back to the appropriate destination, such as registers or memory. This stage updates the CPU's state based on the outcome of the instruction execution. Each of these stages operates concurrently, and the CPU can process multiple instructions simultaneously by overlapping their execution across different stages of the pipeline. As one instruction moves from one stage to the next instruction enters the pipeline, allowing for a continuous flow of instruction processing. In a well-designed pipeline CPU, the stages are carefully balanced to ensure that each stage can complete its work in a single clock cycle. This allows for high throughput and efficient utilization of CPU resources. However, pipeline stalls can occur if there are dependencies between instructions, such as data hazards or control hazards, which may require the CPU to temporarily pause or flush the pipeline until the issue is resolved. Overall, pipelining is a powerful technique for improving CPU performance by parallelizing instruction execution and maximizing the utilization of CPU resources. It has become a fundamental feature of modern CPU architectures, enabling them to achieve high levels of efficiency and throughput. Overlapping instruction execution, also known as instruction-level parallelism, ILP, refers to the ability of a CPU to execute multiple instructions simultaneously by overlapping their execution across different stages of the pipeline or by executing them out of order. This technique allows the CPU to maximize its utilization and improve overall performance by exploiting available parallelism within the instruction stream. There are several ways in which overlapping instruction execution can be achieved. 1. Pipeline parallelism. In a pipeline CPU, multiple instructions are processed concurrently by dividing the instruction execution process into sequential stages. While one instruction is being executed in one stage, the next instruction can enter the pipeline and begin execution in the subsequent stage. This overlapping of instruction execution allows the CPU to achieve higher throughput and better utilization of resources. 2. Superscalar execution. Superscalar CPUs have multiple execution units capable of processing multiple instructions simultaneously within the same clock cycle. These execution units can operate independently and execute different instructions concurrently, allowing for greater instruction-level parallelism and faster overall execution. 3. Out-of-order execution. In out-of-order execution, the CPU dynamically reorders instructions based on their data dependencies and availability of resources to maximize parallelism and improve performance. Instructions are executed as soon as their operands are available, rather than strictly following the original program order. This allows the CPU to keep its execution units busy and avoid pipeline stalls due to dependencies between instructions. 4. Speculative execution. Speculative execution involves predicting the outcome of conditional branches and executing instructions speculatively along the predicted path before the branch outcome is known. If the prediction is correct, the speculatively executed instructions contribute to overlapping instruction execution and improve performance. If the prediction is incorrect, the speculatively executed instructions are discarded, and the correct path is followed instead, by overlapping instruction execution through techniques such as pipeline parallelism, superscalar execution, out-of-order execution, and speculative execution, modern CPUs can achieve higher levels of performance and efficiency. These techniques enable the CPU to exploit available parallelism within the instruction stream and make better use of its resources, resulting in faster execution of programs and improved overall system responsiveness. Pipelining is indeed a fundamental technique used in modern CPU design to improve instruction throughput and overall performance. It involves breaking down the instruction execution process into sequential stages and processing multiple instructions simultaneously by overlapping their execution across different stages of the pipeline. Pipelining was first implemented in supercomputers during the 1980s, where the need for high performance and efficient use of resources drove the development of advanced CPU architectures. Since then, pipelining has become ubiquitous and is now found in virtually all types of CPUs, ranging from high-performance processors used in supercomputers and servers to low-cost microcontrollers like Microchip Technology's PIC series. The widespread adoption of pipelining in CPU design underscores its effectiveness in enhancing performance and efficiency. By allowing multiple instructions to be processed concurrently and making better use of available resources, pipelining enables CPUs to achieve higher levels of instruction-level parallelism and improve overall throughput. In recent years, pipelining has remained a key contributor to CPU performance improvements, second only to memory caching. Memory caching helps reduce memory access latency by storing frequently accessed data closer to the CPU, while pipelining optimizes the execution of instructions by overlapping their processing, thus maximizing the utilization of CPU resources and accelerating program execution. Overall, pipelining plays a crucial role in modern CPU architecture and is instrumental in delivering the high levels of performance and efficiency that users expect from today's computing systems, from supercomputers to embedded devices. Its widespread adoption and continued optimization underscore its importance as a fundamental technique for enhancing CPU performance. The depth of a CPU's instruction pipeline, or the number of stages into which the instruction execution process is divided, determines the level of overlap that can be achieved. Early CPUs often had relatively simple pipelines with only 3 or 4 stages, while modern CPUs have significantly deeper pipelines with 20 stages or more. Here's how the depth of a CPU's pipeline affects its performance. 1. Shallow pipelines. CPUs with shallow pipelines have fewer stages, which means that each stage performs a broader range of tasks. While shallow pipelines are easier to design and manage, they may not achieve as much overlap between instructions, limiting their ability to exploit instruction-level parallelism efficiently. 2. Deeper pipelines. CPUs with deeper pipelines have more stages, allowing for finer-grained control over the instruction execution process. Deeper pipelines enable greater overlap between instructions, as each instruction can progress through more stages simultaneously. This increased overlap improves throughput and performance by making better use of the CPU's resources. The ARM11 CPU, found in the original Raspberry Pi, features an 8-stage instruction pipeline, which was considered relatively deep compared to earlier designs. This depth allowed for more overlap between instructions and contributed to the CPU's performance and efficiency. In contrast, many current Intel processors feature pipelines with 20 stages or more. These CPUs leverage even deeper pipelines to achieve higher levels of instruction-level parallelism and further optimize performance. However, deeper pipelines also introduce challenges such as increased complexity, longer pipeline latency, and potential pipeline stalls. Designers must carefully balance the benefits of deeper pipelines with these challenges to ensure that the CPU achieves optimal performance while maintaining efficiency and reliability. Pipeline hazards are conditions or events that disrupt the smooth flow of instructions through a CPU pipeline, leading to delays or stalls in instruction execution. These hazards can arise due to various factors, including dependencies between instructions, resource contention, and structural limitations of the pipeline architecture. When a hazard occurs, the CPU may need to stall the pipeline temporarily until the issue is resolved. There are 3 main types of pipeline hazards. 1. Data hazards. data hazards occur when an instruction depends on the result of a previous instruction that has not yet completed its execution. There are three types of data hazards. First, read after write, raw, hazard. A later instruction tries to read data that has been written by an earlier instruction that has not yet completed its write operation. Second, write after read, war, hazard. A later instruction tries to write data before a previous instruction has completed reading it. Third, write after write, WAW, hazard. Two instructions try to write to the same register or memory location in quick succession. 2. Control hazards. Control hazards occur when the pipeline encounters a branch or jump instruction whose outcome is not yet known. The CPU must stall the pipeline until the branch outcome is resolved to ensure that instructions are executed in the correct program order. 3. Structural hazards. Structural hazards occur when multiple instructions require access to the same hardware resource at the same time. For example, if two instructions need to access the same execution unit or memory port simultaneously, a structural hazard occurs, and the CPU may need to stall one of the instructions until the resource becomes available. To mitigate pipeline hazards and reduce pipeline stalls, CPU designers employ various techniques such as forwarding, also known as data bypassing. Forwarding allows the CPU to forward data directly from the output of one pipeline stage to the input of another, bypassing the need to wait for the data to be written to a register or memory. Branch prediction. Branch prediction techniques aim to predict the outcome of conditional branches before they are resolved, allowing the CPU to speculatively execute instructions along the predicted path and reduce the impact of control hazards. Instruction reordering. In out-of-order execution architectures, the CPU dynamically reorders instructions to avoid data hazards and maximize instruction-level parallelism. By implementing these techniques and optimizing the pipeline design, CPU designers strive to minimize pipeline hazards and maximize the throughput and efficiency of modern CPUs. The three general categories of pipeline hazards. 1. Control hazards. These hazards arise due to conditional branch instructions, where the outcome of the branch is not known until later in the pipeline. When the CPU encounters a branch instruction, it may need to stall the pipeline until the branch outcome is determined. This ensures that the instructions following the branch are executed correctly according to the program flow. Techniques like branch prediction and speculative execution are employed to mitigate the impact of control hazards and minimize pipeline stalls. 2. Data hazards. Data hazards occur when there is a dependency between instructions regarding the data they operate on. These dependencies can lead to hazards such as read after write, raw, write after read, war, and write after write, WAW, where instructions need to wait for the results of previous instructions before proceeding. Forwarding techniques, also known as data bypassing, are used to alleviate data hazards by forwarding data directly from the output of one stage to the input of another, bypassing the need to wait for the data to be written to memory or registers. 3. Structural hazards. Structural hazards arise due to conflicts over hardware resources within the CPU pipeline. For example, if multiple instructions require access to the same execution unit or memory port simultaneously, a structural hazard occurs, and the CPU may need to stall one of the instructions until the resource becomes available. Increasing the number of resources or employing techniques like resource scheduling can help alleviate structural hazards and improve pipeline efficiency. By identifying and mitigating these pipeline hazards, CPU designers aim to optimize pipeline performance and maximize instruction throughput. Techniques such as instruction scheduling, hardware interlocks, and cache optimizations are employed to minimize the impact of hazards and ensure smooth and efficient execution of instructions. Control hazards, particularly arising from conditional branch instructions, pose a challenge in maintaining the sequential execution of instructions in a CPU pipeline. When a conditional branch instruction is encountered, the CPU may need to stall the pipeline until the outcome of the branch is determined. However, as you pointed out, this stall introduces inefficiencies because instructions that have already been fetched and decoded may no longer be relevant to the program's execution if the branch is taken. To address this issue and maintain the illusion of executing instructions one at a time, the CPU employs techniques such as branch prediction and speculative execution. 1. Branch prediction. Branch prediction techniques aim to predict the outcome of a branch instruction before it is actually resolved. Based on historical behavior or patterns observed in the program's execution, the CPU predicts whether the branch is likely to be taken or not taken. If the prediction is correct, the CPU can speculatively continue fetching and executing instructions along the predicted path, thereby avoiding pipeline stalls. 2. Speculative execution. In speculative execution, the CPU proceeds to execute instructions speculatively along the predicted branch path, even before the actual branch outcome is known. Instructions are executed out of order, and the CPU maintains a reorder buffer to ensure that the results are committed to architectural state in program order. If the prediction turns out to be incorrect, the speculatively executed instructions are discarded, and the correct path is followed instead. By using branch prediction and speculative execution, the CPU can minimize the impact of control hazards and maintain efficient pipeline operation. These techniques help reduce pipeline stalls and ensure that the CPU remains busy executing instructions, even in the presence of conditional branches that might otherwise disrupt the flow of program execution. Overall, effective management of control hazards is essential for optimizing CPU performance and throughput. Branch prediction and speculative execution are indeed two closely related mechanisms employed by most modern CPU architectures to mitigate the impact of pipeline hazards, particularly control hazards arising from conditional branch instructions. 1. Branch prediction. Branch prediction techniques aim to predict the outcome of a branch instruction before it is actually resolved. By analyzing past behavior or utilizing sophisticated algorithms, the CPU predicts whether a branch is likely to be taken or not taken. Predictions are made at various stages of the pipeline, allowing the CPU to speculatively fetch and execute instructions along the predicted branch path. Branch prediction helps reduce the likelihood of pipeline stalls by allowing the CPU to continue executing instructions without waiting for the actual branch outcome. 2. Speculative execution. Speculative execution goes hand in hand with branch prediction. Once a branch is predicted, the CPU may speculatively execute instructions along the predicted branch path, even before the branch outcome is known. This allows the CPU to maintain a high level of instruction-level parallelism and keep the pipeline busy. Speculatively executed instructions are tracked and executed out of order, and a reorder buffer ensures that the results are committed to architectural state in program order. If the prediction turns out to be correct, the speculatively executed instructions contribute to overall performance gains. If the prediction is incorrect, the CPU discards the speculatively executed instructions and resumes execution from the correct path. By combining branch prediction and speculative execution, modern CPU architectures effectively mitigate the impact of control hazards and maintain efficient pipeline operation. These techniques allow CPUs to achieve high levels of instruction throughput and performance, even in the presence of complex branching behavior within programs. Data hazards, also known as data dependencies, occur when instructions in a CPU pipeline require data that is not yet available because it is produced by a previous instruction that has not yet completed its execution. This situation can lead to incorrect results if not properly handled. There are three main types of data hazards. 1. Read after write, RAW, hazard, occurs when a later instruction needs to read data that is produced by an earlier instruction that has not yet finished writing the data. If the later instruction proceeds without waiting for the earlier instruction to complete, it may use stale or incorrect data, leading to erroneous results. 2. Write after read, WAR, hazard, occurs when a later instruction writes data to a location that is being read by an earlier instruction. If the later instruction writes the data before the earlier instruction completes reading it, the earlier instruction may end up using stale or incorrect data. 3. Write after write, WAW, hazard, occurs when two instructions write to the same location in memory or register in quick succession. If the second instruction writes the data before the first instruction completes its write operation, the data written by the first instruction may be overwritten prematurely. To mitigate data hazards and ensure correct execution of instructions, CPUs employ techniques such as data forwarding, also known as data bypassing, and stalling, data forwarding. In data forwarding, the CPU forwards data directly from the output of one pipeline stage to the input of another, bypassing the need to wait for the data to be written to memory or registers. This allows instructions to access the most up-to-date data and helps mitigate data hazards by reducing the latency associated with data dependencies. Stalling: if data forwarding is not possible or if the hazard cannot be resolved in time, the CPU may need to stall the pipeline temporarily until the data becomes available. During a stall, the CPU does not fetch or execute new instructions, allowing time for the required data to be produced by the earlier instruction. By employing these techniques, CPUs can effectively manage data hazards and ensure correct execution of instructions in the pipeline. This allows for efficient utilization of CPU resources and helps maintain the integrity of program execution. Structural hazards occur when two or more instructions in the pipeline require access to the same hardware resource at the same time. This can lead to contention for resources and potential conflicts that may disrupt the smooth execution of instructions. To mitigate structural hazards and resolve resource conflicts, CPU designers employ various techniques. 1. Resource partitioning. One approach to addressing structural hazards is to partition or separate resources that are commonly contended. For example, splitting the unified level 1 cache into separate caches for data and instructions can help reduce conflicts between instructions that require simultaneous access to memory. 2. Interlocks. Interlocks, also known as hazard detection units, are hardware components responsible for detecting potential hazards in the pipeline. These units monitor the progress of instructions through the pipeline and identify situations where hazards may occur, such as data dependencies or resource conflicts. When a hazard is detected, the interlock inserts a bubble, also known as a pipeline stall, ahead of the problematic instruction. This delay allows earlier instructions to complete their execution before conflicting instructions reach the critical resource. 3. Pipeline bypassing. Similar to data forwarding, pipeline bypassing allows data to be passed directly from one stage of the pipeline to another. Bypassing intermediate stages. This can help alleviate structural hazards by reducing the need for instructions to contend for shared resources. 4. Resource scheduling techniques aim to schedule instructions in such a way that conflicts for shared resources are minimized. By carefully orchestrating the execution of instructions, resource scheduling can help mitigate structural hazards and improve overall pipeline efficiency. The ARM11 CPU employs a pipeline architecture consisting of 8 stages to facilitate the execution of instructions efficiently. Let's delve into the stages of the ARM11 pipeline. 1. Fetch, F, stage. In this stage, the CPU fetches the next instruction from memory using the program counter, PC. The instruction is fetched from memory into the instruction cache for further processing. 2. Decode, D, stage. In the decode stage, the fetched instruction is decoded to determine its type and the operations it entails. This stage prepares the instruction for execution and identifies any associated operands or data dependencies. 3. Execute, E, stage. The execute stage is where the actual computation or operation specified by the instruction takes place. This can involve arithmetic operations, logical operations, memory accesses, or control flow changes. 4. Memory, M, stage. If the instruction requires memory access, such as a load or store operation, the memory stage handles this access. Data is read from or written to memory during this stage, and any necessary data forwarding or cache operations are performed. 5. Write back, W, stage. In the write back stage, the results of the executed instruction are written back to the appropriate destination, such as registers or memory. This stage updates the CPU's state based on the outcome of the instruction execution. 6. Branch, B, stage. If the instruction is a branch or jump instruction, the branch stage calculates the target address of the branch and prepares the CPU to handle the branch outcome. 7. Interrupt, I, stage. the interrupt stage handles interrupts and exceptions that may occur during instruction execution. It prioritizes and manages the handling of interrupts to ensure proper program execution. 8. Coprocessor, C, stage. If the instruction involves coprocessor operations or interactions with specialized hardware units, the coprocessor stage manages these operations. Superscalar execution represents a significant advancement in CPU design, enabling the simultaneous execution of multiple instructions to achieve true parallelism and maximize instruction throughput. In a superscalar CPU, instructions are fetched from memory in groups, typically pairs, and examined to determine if they can be executed in parallel without dependencies. If two instructions can be executed independently, the CPU dispatches them to separate execution units, often referred to as functional units or execution pipelines. These execution units specialize in different types of operations, such as integer arithmetic, floating-point arithmetic, or vector operations, allowing the CPU to exploit diverse types of parallelism within the instruction stream. The goal of superscalar execution is to keep all available execution units busy as much of the time as possible, thereby maximizing instruction throughput and overall CPU performance. By executing multiple instructions simultaneously, superscalar CPUs can achieve higher levels of instruction-level parallelism and improve program execution speed. While the ARM11 microarchitecture does not support superscalar execution, subsequent generations of ARM processors, such as the Cortex-A series, introduced superscalar capabilities. The Cortex-A family of processors features superscalar architectures capable of issuing multiple instructions per cycle, with some models supporting the simultaneous execution of 4 or more instructions. This advancement in CPU design enhances the performance and efficiency of ARM-based systems, making them well-suited for a wide range of computing tasks, from mobile devices to high-performance computing applications. SIMD instructions are indeed a powerful mechanism for exploiting parallelism in modern CPUs, allowing for the simultaneous processing of multiple data items using a single instruction. Here's a breakdown of how SIMD instructions work. 1. Vectorization. SIMD instructions operate on vectors of data, where a vector typically consists of multiple elements, such as 4 floating-point numbers or integers. These vectors are loaded from memory into special SIMD registers, which are designed to hold multiple data elements. 2. Parallel execution. Once the vector data is loaded into SIMD registers, a single SIMD instruction performs the same operation simultaneously on all elements of the vector. This means that a single addition, subtraction, multiplication, or division operation is applied to each element of the vector in parallel. 3. Vectorization width. In many CPU architectures, SIMD instructions process vectors of 4 elements at once. However, some architectures may support wider vectors, allowing for even greater parallelism. For example, AVX512 instructions in Intel processors can operate on vectors of up to 512 bits wide, which translates to 16 double-precision floating-point numbers or 32 single-precision floating-point numbers. 4. Memory access. After the SIMD operation is performed on the vector data, the resulting vector is often written back to memory. This allows SIMD instructions to efficiently process large datasets in parallel, such as image processing, signal processing, and scientific computing tasks. By leveraging SIMD instructions, software developers can significantly accelerate performance-critical computations by exploiting parallelism at the instruction level. SIMD instructions are widely used in applications that require intensive numerical calculations, such as multimedia processing, scientific simulations, and machine learning algorithms. The ARM11 core in the original Raspberry Pi supports SIMD, single instruction, multiple data, instruction execution in a limited manner, known as Neon technology. Neon allows the ARM11 processor to perform SIMD operations on 32-bit data words, with each 32-bit word treated as 4 separate 8-bit values. While this approach may seem limited compared to SIMD implementations on other architectures that support wider vector sizes, such as 128-bit or 256-bit vectors, It still offers significant benefits, especially in graphics and audio processing tasks where operations on 8-bit quantities are common, by treating each byte within a 32-bit word as a separate value. The ARM11 core can perform SIMD operations on multiple elements simultaneously, effectively increasing computational throughput and improving performance in tasks that involve parallel processing of small data elements. While Neon technology on the ARM11 core may not offer the same level of parallelism as wider SIMD implementations, it still provides a valuable tool for accelerating certain types of computations on the Raspberry Pi platform, particularly in multimedia and signal processing applications where operations on 8-bit quantities are prevalent. The ordering of bytes in memory is a fundamental aspect of computer architecture and is known as endianness. Endianness refers to the byte ordering scheme used to store multi-byte data values in memory. There are two main types of endianness: big endian. In a big endian system, the most significant byte, MSB, of a multi-byte data value is stored at the lowest memory address, while the least significant byte, LSB, is stored at the highest memory address. This means that when you access a multi-byte data value in memory, you start reading from the highest address down to the lowest address, little endian. In a little endian system, the least significant byte, LSB, of a multi-byte data value is stored at the lowest memory address, while the most significant byte, MSB, is stored at the highest memory address. This means that when you access a multi-byte data value in memory, you start reading from the lowest address up to the highest address. The choice of endianness can have implications for software compatibility and data interchangeability between systems. For example, big endian systems are often favored in networking protocols and file formats because they provide a natural ordering for multi-byte data values that matches the convention of writing numbers from left to right, MSB to LSB. Little endian systems are commonly used in x86-based processors and Windows operating systems, while little endian ordering can be more efficient for certain operations. It can lead to compatibility issues when exchanging data with big endian systems. Some architectures, such as ARM, provide support for both big endian and little endian modes, allowing flexibility in system design and data interchangeability. Overall, understanding endianness is essential for software developers and system architects to ensure proper handling of multi-byte data values and compatibility between different systems and platforms.